Welcome to Gem A Live. I'm Julia Griffith, and today we're going to be talking about fluorescence. So let's dive straight into it, shall we? We're going to cover some learning objectives first of all. So, firstly, we're going to be discussing what fluorescence is. So, we're going to talk about the history and also the science of fluorescence, so the chemistry and physics. It's quite a small section though, so bear with me if you're not particularly science minded, but it will be very interesting. We're also going to discuss how to test for fluorescence, so focusing on those pieces of equipment that we can actually view the fluorescence of gems under, and also talk about good practices. We're going to talk about how we use fluorescence within gemology. So we're going to focus on just a few really specific examples, mainly because in gemology, gemstones and minerals, there is such a huge variety in results that you can get from gem to gem. Even within one gem variety, it can vary. So we're going to just focus on a few key things that can help you with your identification and testing. And then lastly, we're going to focus on diamond fluorescence, as this is a large topic in itself. So we're going to start off with some definitions. So starting with fluorescence itself. So fluorescence is the emission of light by a substance whilst it's being excited by a higher energy. And so if we focus on this picture here, this is a piece of fluorite just in daylight. And if we excite it with a higher energy, which in this case is long wave UV light, we will actually see that the gemstone itself starts to glow. And this glowing is actually an emission of light by the fluorite itself, and it's actually emitting this purple blue color. And this is what's known as fluorescence. If there is a delay in this effect, so if it's seen after the excitation source has been removed, then this is what's known as phosphorescence. So this is the emission of light by a substance after it's been exposed to a higher energy. But if we talk a little bit about the history of fluorescence, so fluorescence has actually been noted for millennia. It was first documented, I believe, in 1500 BC, where it was actually used as a medicine. So it would be these organic wood resins, I think, within a liquid. And this would actually glow a blue color. So everyone thought that it had medicinal, magical properties and would use it as a medicine. But the science really was defined by Sir George Gabriel Stokes. He was the one who really did a lot of research into fluorescence and other luminescences as well. And he made up the word, he coined the word fluorescence as well. So in 1852, the word fluorescence then started being picked up and used across a number of sciences. So fluorescence is actually made up of two different words. So fluorspar, which is fluorite, makes up the first part. That is because Sir George Gabriel Stokes noted that a number of fluorite specimens show very strong fluorescence in this purplish blue colour. The rest of it is actually was taken from opalescence because that is also an effect that he believed it started to mimic. So if we have a look at these pictures here, so the first picture, this is a range of fluorites. As you can see, I've got all sorts of colors, some without color completely, so colorless to colored, all these different banded materials. And under long wave UV light, it doesn't matter what color they are in daylight, they can actually fluoresce, and they fluoresce a very consistent purplish blue color. Now, Sir George Gabriel Stokes, he also came up with a law of physics, which is the Stokes law of fluorescence. And this basically says that any fluorescence emitted by an object will always be of a lower wavelength than the excitation source. But to understand that, we're going to look into a bit of the science. So starting off with the electromagnetic spectrum. And the electromagnetic spectrum is a distribution of all the electromagnetic energies that we have. And we are actually previewed, as humans, we're previewed to a really small section of this known as visible light. I've been quite generous here, but actually it makes up 0.00035, I think, percent of the whole spectrum. It's a really, really small section of wavelengths that we're able to see. And Visible light runs from 400 to 700 nanometers, 400 being the violet, 700 being red. And when we see these wavelengths all together, it looks like white light to us. So this is what we get from the sun. Of course, we can disperse this white light into all the colors of the rainbow. Now, if we go up the spectrum, so beyond the red, we actually enter these lower energy wavelengths. So starting with infrared and then into microwaves and even goes on into radio waves. So these are much longer wavelengths. By the time you're in radio waves, they can be kilometers long in wavelength, much lower frequency and also much lower energy. If we go the opposite direction in the spectrum, so beyond the violet, we go into the ultraviolet and then into the X-ray and then into the gamma rays. And the more that we go into this spectrum, you'll actually see shorter and shorter wavelengths. And with these shorter wavelengths, the frequency increases, and this actually gives a lot higher energy. So much so that it's actually extremely dangerous for us. So, when we're focusing on the electromagnetic spectrum for use in gemology, although, well, actually, a number of it can be used in gemology, for fluorescence, we're mainly concerned with the ultraviolet section of this spectrum. X-ray fluorescence is sometimes used. For example, it's used in the mining and recovery of diamonds because we have X-ray separators, and these work on the fact that all diamonds will fluoresce under X-ray. So during the recovery process, when you've got all this crushed ore that will be studded with diamonds, they actually use X-rays to fluoresce all the diamonds so that they can actually be separated out. Really good use of fluorescence and X-ray. But most of the time, actually, we're just going to use UV. So let's focus in a little bit closer on just this ultraviolet light portion of the electromagnetic spectrum. So here we have visible light and ultraviolet. We do actually have different wavelengths. So visible light, as I said, it runs from 400 to 700 nanometers. UV runs from 10 to 400 nanometers. And actually, we separate UV into two different types of ultraviolet light when it comes to gemology. One is shortwave UV. So this is actually a smaller range of wavelengths running from 10 nanometers to 300 nanometers. But during gem testing, we actually just use one principal wavelength, and this will be at 254 nanometers. The reason that we just use one wavelength in testing is so that it brings some consistency to the method of testing. If we were to just use a range of shortwave UV light or different ones each time, well, you would certainly get different results every time as well. The other type of UV light that we use is long-wave UV light, and this has a wavelength range of 300 to 400 nanometers, and we use the principal wavelength of 365 nanometers. But when it comes to fluorescence, we're actually going to talk a bit about ultraviolet light in regards to energy as well, because I keep saying these higher energies. It's hard to see these higher energies when we look at just wavelengths. So let's have a look at how this translates into energy. So the visible light range from violet to red actually runs from 3.1 electron volts to 1.77 electron volts. So a very narrow band of energy. When it comes to UV, this actually runs from 3.1 electron volts to 124 electron volts. So short wave, so let's say 10 nanometers equals 124 electron volts. That's a lot of energy. No wonder it's harmful to us. If we have a look at which wavelengths we use for testing, for shortwave UV, we're actually going to use the energy of 4.88 in regards to testing, and in regards to long wave, we use the energy of 3.44. So doesn't seem too far away from visible energies, but actually it is a lot more dangerous for us, especially that shortwave. But I'll talk to you about care and caution whilst testing a bit later. So when it comes to fluorescence, as I said before, higher energy wavelengths are going to be absorbed by a material and then emitted as a lower energy wavelength. So basically, we're going to take this UV light and apply it to an object and the object absorbs this light but then re-emits it in the visible light range. And this is how we can see it. So basically, our gemstones are taking invisible light and turning it into visible light. And depending on which energy it kicks out at us, we will actually see the varying colors of fluorescence. To explain this in a bit more detail, we're going to zoom in to an atom now. So here, what you can see is this is an electron during different stages of excitation. We're going to start with this first electron here. So when it's not under high energy, it's in a particular energy band, which we're going to call the ground state for this electron. So fluorescence is all to do with the movement of electrons. Okay, so here's our first electron. Now, when we actually apply high energy to it, let's say long wave, which is that 365 nanometers, energy of 3.4 electron volts, this is when the electron has enough energy to be excited up to the higher energy bands. So this is when it's in its excited state. Now, during this or after this has happened, basically what will happen is the electron will start to relax and it will actually slowly come down these energy levels to slowly return back to the ground state. So as it actually returns down these excited states, it releases energy. So it loses energy essentially, and this is in heat or vibrations. So then by the time that it actually is just in the lower stage of the excited state, it's lost energy. Let's say it's lost half an electron volt. Then when it returns to its ground state, this is when the electron releases all of that excess energy back out of the gem. So 3.4 electron volts minus 0.5 electron volts is 2.9 electron volts. This translates to 427 nanometers, which if you think of your spectrum, is within the violet to blue range. So this is when it actually kicks out blue fluorescence. Now this actually happens really fast and it happens on a very big scale. So lots of electrons inside our gemstone going from the ground state up to the excited state, releasing a little bit of energy. And then as it returns the rest of the energy, that's when it's letting out fluorescence. And this is happening the whole time that it's under excitation. Now, if there is a delay can happen, and that's actually due to section 3 here. There can be a delay in the release of energy or the relaxation state. Basically, it's all to do with the different ways that the electron can relax within the structure. It may actually be a delay, and if there's a delay, that's what's known as phosphorescence. So fluorescence, if it's all happening instantaneously, and then if there's a delay which continues after the light source is removed, we have phosphorescence. And as you'll notice as well, or I hope that you've noticed, so this is actually the amount of energy that's lost at stage number 3. This is actually what then governs what color the fluorescence will be. So let's say if I lost 1.5 electron volts and went down to 1.9 electron volts here, I would actually be fluorescing red. So it's all to do with how much energy is released at that stage, and that completely depends on the gemstone itself. So let's have a look into what actually causes the fluorescence. Fair warning, this is very complex and actually very much not fully understood. So there's lots of research into it, but it can be so confusing and there's no one rule fits all, it seems. However, there are common consensus that the main reason for fluorescence is actually due to impurities within the structure. And if an impurity causes fluorescence, this is known as a fluorophore, which is also known as an activator. And there are many transitional elements that will cause fluorescence. Here's a list of them. So chromium, uranium, manganese, lead, boron, tungsten, titanium, and rare earth elements. For example, molybdenum is a common one. And these are all elements that, if in a structure, can actually induce fluorescence into the stone during the excitation of the stone. There are some other rare earth elements as well, which I'll just list here. There are also impurities which actually can quench fluorescence. These are known as quenchers, and quenchers basically suppress or completely eliminate fluorescence within the stone. So these elements, again, they're all transitional elements, iron, nickel, and copper. If these are within a gemstone, they may actually stop fluorescence altogether or just suppress the fluorescence that might be seen otherwise. So these actually come into knowing your fluorophores and your quenchers can be very handy when testing gems, especially if you know the chemical composition of them. Other causes of fluorescence that we know about, defects within the crystal structure can cause fluorescence. For example, you get vacancies such as nitrogen vacancies. These can cause fluorescence in diamonds. And also, organic impurities can cause fluorescence as well. I'm sure when you're in the club, you might see that your teeth start fluorescing. That's all to do with amino acids within your dentine, causes your teeth to fluoresce white under long wave UV. And many organic gemstones also show fluorescent effects as well. So now let's just focus a little bit on UV light sources. You might know quite a lot about these, but just to run through them. Warning before we start, shortwave UV light is dangerous. You should never put any part of your skin under UV light. So do make sure that your light source is always turned off before you put your hands in to any of the range of the light source. Also for long wave and short wave, don't wave it around, never get it in your eyes because actually that can cause quite a lot of damage due to those higher energies. But different light sources that we can have. So here is a UV box. This is one of the, or by far really, the best piece of equipment for testing fluorescence because it gives you that perfect environment for testing. It's dark, it's shielded from any excess light. Even the eye section is shielded from excess light. And it tests for both shortwave and longwave UV. So this really is, the best tester really for testing fluorescence. We can also have portable fluorescents, so great if you are out and about. These ones must be used with caution. I recommend protective eyeglasses as well, because there is nothing protecting you from this source. So you have to use it very, very carefully, but you can test shortwave and longwave with these devices, which can be very handy. And then also we have your UV pen torch, which if you are a student of GEMA, you'll be very familiar with this. But these just show long wave UV, but can be really handy where quite a lot of gems do show fluorescence effects under long wave. Can be really handy just for quickly testing your gems to see if they fluoresce. So when we test fluorescence, good practices to have. We must use dark surroundings. The main reason for that is that a white background actually fluoresces itself because, paper fluoresces. So make sure you use a dark background, non-reflected, shielded away from any excess light. If you can, turn off all your other light sources so that you can really see the fluorescence from your gem because sometimes they're really subtle. If your stone is faceted, make sure that you place the stone face down. Main reason for that is that gems such as diamonds are actually excellent at reflecting light back at you. So this can actually make the diamond seem more reflective than it actually is. And also when you're testing, especially if you're testing a lot of gems in one sitting, be consistent with your distance away from the light source. So that distance between the gem and the light source needs to be consistent. The reason for that is often the closer the light source, the brighter the gem fluoresces. So you want to kind of bring a bit of consistency to your methodology when testing. So for the pen particularly, I recommend maybe an inch or two away. But whatever you choose, make sure you're consistent. And then when you record your results, you actually want to record a number of different things. So the light wave that you're actually testing it under, so whether it's short wave or long wave, the color of the fluorescence, and also the strength of the fluorescence. So whether it's strong, medium, moderate, weak, what have you. I actually looked back, sorry, a side note, I looked back at some of my testing recently for fluorescence and actually I didn't write the colour at all. So actually, when I look back at my notes, I found it really unhelpful. So that's why always full reports that you should, when you report your results, give it nice and comprehensively. So let's just have a look at some fluorescent gemstones. Fair warning, this is not a complete list because, there's organic gems which aren't on here, organic gems, many of them fluoresce. Also, a lot of the rarer minerals that can still be used as gemstones are also not on this list. Even the ones that are on this list, there might be exceptions within their varieties which may not fluoresce. So the key thing really for fluorescent gemstones to note, not to scare you, but there is very little predictability with the fluorescence of gemstones. There's a huge variance. So therefore, even though it can be very helpful on particular occasions, and it can be very helpful, even then there are exceptions to the rules. So basically, when we learn about fluorescence, my advice would be to learn just a few key things first of all, and then build on this knowledge over time. And often that will be with what's important to you at the time. So, what you're testing or what you need to learn about at the time. And you'll see it slowly builds. But otherwise, I don't know anyone that does know every single fluorescence response. I think it would be quite a commitment to learning to actually get all of those in. So let's actually talk about how we can use fluorescence. The good thing about fluorescence is that we can use it on pretty much everything. So we can use it on set stones, loose stones, rough stones, cut stones. It will give you clear results if you use it in the right setting. We can also test many stones at once, which can be so helpful, particularly if you're buying in bulk or if you have to sort out lots of things, let's say maybe at a pawnbroker's or at an auction house. So fluorescence can be really quick, effective, easy to test with. When it comes to what it can tell us, it can aid the identification of gems, but quite often there are so many exceptions, we have to do research really and make sure that there are no exceptions to that rule. But some gemstones have a more consistent response, so they're the ones that we're going to focus on today in this session. There are some treatments that can be identified with fluorescence and some composites and some synthetics. So we're going to look at a few slides to show you those in a second. Also, fluorescence can indicate locality for your different gems. So this is, again, only on a few occasions, but this can also be really helpful. Also, fluorescence can help during mining. I've already given the diamond X-ray example, but there are more examples as well. And lastly, they are also very good for display. Actually, if you go into any museum, pretty much anywhere in the world, if they have a mineral gallery, they will likely have a display of these fluorescent gems because where they're turning invisible light into visible light, they look like they glow in the dark. And that is just fascinating to us. So let's have a look then at some really particular examples. And we're going to start off just focusing on some red stones, first of all. So here, my red stones, all in daylight, and here they are under long wave UV. As you can see, some are fluorescing red, one is fluorescing very strongly in the middle there, and then a couple are not fluorescing at all. Now, often the results of a gem won't necessarily point to one identity, but it can support an identity and eliminate other possibilities. So, for example, in red gems, let's just think of some red gems. Well, we have ruby, which under long wave will fluoresce weak to bright red. So, we might have some rubies in here. We have synthetic ruby, which fluoresces very bright red. I have an idea which one might be synthetic here. Then spinel also fluoresces bright red. So, okay, out of the red fluorescent gems that we have here, we have, well, two different species that it could be. It could either be spinel or it could be corundum, so ruby. Other red stones, garnets, well, these are inert. So, okay, we might have some garnets here. And then also red glass is also inert. So with this test, with this picture as well, we haven't necessarily identified the stone, but we kind of know that all of the ones that are fluorescing red are going to be either ruby and spinel, or spinel, sorry, and then the ones that are not fluorescing are either going to be garnet or glass. So it's not giving you an identity, but it's certainly supporting or eliminating possibilities. In regards to how this is helpful in the trade, For example, if I was being sold a ruby and I only had a UV pen with me, if I applied the UV pen to the stone and it didn't fluoresce at all, I would start being suspicious. Okay, so that's how it can help. Now, when it comes to shortwave, oh, just to give you actually the identities of these stones, that would be nice, wouldn't it? So the first one was a spinel, the second one was red glass, so paste. Third one was synthetic Vinoy flame fusion ruby. These are the ones that can really go very bright red. Other synthetic rubies go pretty bright red as well, but none quite as much as the flame fusion kind. Then we have an almandine pyrope garnet, and then two natural rubies. So that's what we actually have just tested there. Now, under shortwave, we have different results again. So if we focus in on the screen here, our first gem is no longer fluorescing, so the spinel is inert. And then we have a variety of gems here. I just remembered I've got it in text. So the ruby will be inert to moderate red. If we focus on the rubies, actually our natural ones, we can no longer see. So these are either inert or a really, really weak red happening here because we can no longer see those stones. Okay. A synthetic ruby, moderate to bright red. So that's this stone just here. Spinel is inert. So this is this one here. So again, for this test, what it's actually given us is it's managed to identify for us the synthetic ruby, and actually the rubies, natural rubies versus the spinel, unfortunately still hasn't given me the correct identity for that with this test. Okay, just to let you know, there is a slight crossover with some natural rubies and synthetic rubies. As you can see, they both can fluoresce moderate under shortwave UV light. These will typically be the ones with low iron content. So for example, those from Burma, they can still have a good fluorescence under shortwave UV. Garnets, they're inert under shortwave UV, but then red glass, if they're coloured by rare earth elements, they actually turn this chalky white colour, which is what you can see here. So actually we have managed to differentiate in this instance between red glass and garnet. So that's quite handy. Be warned though that other red glasses, so for example those coloured by gold or selenium, will have a different response. Let's focus now on some treatments because on some occasions treatments can be completely identified. This can be really handy. So dyes might be able to be identified particularly if they are coloured by one of those fluorophore elements, okay, for example, chromium. Fillings can also be identified if the filling is fluorescent, so that can be very handy. Also, we can identify high temperature heat treatment in corundum and also diffusion treatment in corundum as well. So the first one we're going to focus on is a dye. So we're going to look at green jadeite versus dyed jadeite. Natural green jadeite is inert to a weak blue under long wave UV light. However, if it's dyed green, and the dye is typically chromium that's used for dyeing jadeite, then actually the dye will have its own fluorescence, which is a very bright green. So therefore will look something like this. So in this picture, all of those spots, areas, they're actually patches of this green chromium dye. It would not look like this if it was naturally green. It would actually be the same color as the rest, or the same strength, sorry, as the rest of the material. So therefore, this is a really good way and one of the more consistent results that you can get for testing fluorescence. So jadeite versus dyed green jadeite. Another treatment we're going to focus on is fillings. So here we're actually looking at a filled emerald. So this emerald is filled with oil. Emeralds typically fluoresce under long wave UV light. They might actually be inert, but if they fluoresce, they'll be this weak reddish color. So you can see that in the main body of the material here. If you focus on either side of this gem, you'll actually see these streaks of blue fluorescence, and these are concentrated in the fractures. So this is actually your oiled area of your gem. So not only are you getting a different color of fluorescence, but where it's concentrated to the cracks, it's a really nice way of seeing that this emerald has been treated, and also in a way to what degree. So that's really, really handy and diagnostic of a filling. When it comes to other fillings that we have, so we focused on this a couple of weeks ago, we do have lead glass filled sapphires and rubies as well. Now, these can fluoresce under long wave and shortwave UV light, but in these photographs, I'm actually showing you ones from the diamond view, which is a very high energy UV light source typically used to differentiate natural from synthetic diamonds. And what we have in our cobalt lead glass filled sapphire, you've actually got this whole network of fluorescent area. And basically what this is your cobalt lead filled glass fluorescing this chalky blue under shortwave. And you'll notice that the rest of the material is not fluorescent, and that's because sapphires do not fluoresce, or colorless sapphires do not fluoresce. When it comes to our ruby, you'll notice straight away actually that the main body of the material is fluorescing. So the ruby is fluorescing this bright red under shortwave. And then also you've got these glass areas that are showing you exactly where the glass is in the cracks, which are also fluorescing this whitish color. So again, a great test for these stones. Under long wave UV, it can be very helpful for your cobalt lead glass filled sapphires because your lead filled glass will actually fluoresce a red color under long wave and the sapphire itself will stay inert. It might be a bit harder for your rubies because your ruby will fluoresce and the glass often doesn't fluoresce much under long wave, so it might be harder for this stone. You might be able to see dead areas of fluorescence, which might indicate that it's been filled, but otherwise you're probably better off with observations on this one. So this is just one treatment or even a composite that can be identified from fluorescence. There are other composites that might be able to be identified with fluorescence as well. So if they are put together, you just need to test them on their side so that you can test the different components and see if they fluoresce differently. So also good for composite stones. Oh, the next treatment we're going to focus on is high temperature heat treatment in sapphire. When it comes to blue sapphires that have been subjected to high temperature heat treatments, so we're typically talking over 1500 degrees centigrade, they end up having this really unique fluorescence, which is different from other natural blue sapphires. And it actually looks like this chalky blue or bluish green fluorescence. So that's really unique to these treated sapphires, and this is seen under shortwave UV. Now, just to let you know what other natural blue sapphires do, typically if they're medium to dark green, they are inert. However, if they are from a particular locality, if they're from either Sri Lanka or Madagascar, the blue sapphires from there actually go this really cool apricot color under long wave and shortwave UV light. So this is the only one that's otherwise natural that goes this color, signifying that it's actually been heat treated with a high temperature heat treatment. The only thing that this could be confused with, so do mind, is a synthetic blue sapphire. Synthetic blue sapphires can also go a chalky greenish blue under shortwave UV light. But don't panic because we can actually use other tests to distinguish between them, for example, observation. So have a look for your natural features versus your synthetic features. Even in this picture, actually, it's showing you that it's a natural sapphire due to that angular and straight color zoning that it's showing you. So don't panic, there are always other ways to figure things out. Let's move on to identifying some other synthetics. So these effects often differ from each gem's natural counterpart. However, a big mixed bag of how they react. So for example, they can cross over in results. Some react the same, only stronger, or some act in stronger under shortwave than long wave, or kind of like the reverse of it. It really does depend on the gem. But I do have a couple of examples for you. But just a warning, always use other tests to back up your conclusions, which you should be doing anyway. It's always good to get lots of evidence. But some examples of synthetics that can be stronger in shortwave rather than long wave, when it's the opposite way round in the naturals. One example is spinel. So here is a synthetic Verneuil green, well, yes, a synthetic Verneuil spinel under shortwave UV. There's actually a number of colors of synthetic spinels that can show a really strong fluorescence in shortwave and then a much lesser or even inert fluorescence under long wave. Natural fluorescence is the opposite way round. If it fluoresces, it will be strongest under long wave and less so, if not inert, under shortwave. Okay, so if you ever do see these green fluorescent colors, this is actually due to the fluorophore manganese. So yeah, pretty cool. Another one that is also stronger in long wave as opposed to, beg your pardon, I keep getting confused. Another stone that is stronger in short wave as opposed to long wave, when the natural is the reverse of that, is diamonds. And we will focus on this towards the end of the session. But to focus on one other type of gem, I'm going to talk about emeralds. So emeralds, naturally, these are typically inert, but they can show weak to moderate red colours under long-wave UV due to chromium content. So they have a range of things that they can do, but inert or to weak moderate red. Originally, when synthetic emeralds were first created, it was great because these actually fluoresced a weak to strong orangey red fluorescence or just a red fluorescence. And very typically it was strong red, just like this here. So actually, when these were first created, it was quite a relief that these were strongly fluorescent so they could quite easily be identified from the natural emeralds. Especially, for example, if you were bulk testing, let's say I had a parcel of green stones, put them under the fluorescent, put them under the long wave UV, and then straight away you'll actually be able to see the ones that glow red and pick those out and test them separately. If they're emeralds, well, they would have been synthetic emeralds. Excellent. However, since then, so since these have first been created, they've been um, experimenting, and now actually they can create inert synthetic emeralds. So here's a photograph of that. So that's a synthetic hydrothermal emerald. This one in particular has been doped with iron, which is one of our quenchers, and therefore this cancels out the chromium fluorophore, actually causing this lack of fluorescence. So it's now inert. So where natural emeralds can also be inert, unfortunately now it's made our job a little bit harder. Synthetic emeralds will also be inert if their colouring element is vanadium as opposed to chromium as well, because vanadium isn't a fluorophore. The one saving grace, though, for testing emeralds is that most of them are filled. So about 98% of emeralds are treated by oiling or even a resin filling. And so oiling will appear either that blue color I showed you earlier in the earlier slide, sometimes a yellowish or a greenish as color as well, or it might appear whitish if it's filled with resin, so photographed here. And this fluorescence will always be concentrated in the cracks. The rest of the emerald might be a dull red or inert, but either way, nice and easily distinguished. So that's our silver lining to testing emeralds. Another way that fluorescence can help us is that it actually can indicate different localities. And for this example, I'm going to focus purely on ruby. The way that this works is all to do with any of those fluorophores in the crystal structure and also any quenchers within the crystal structure. So if we start with rubies from Myanmar, so Burmese rubies, these typically have a really strong fluorescence under long wave and then a moderate red under shortwave. So often these are described as glowing under long-wave fluorescence. So these can actually be confused with the Verneuil flame fusion. They can be so strong. So when they say strong, they mean strong in this instance, okay? So that's the fluorescence of your Burmese rubies. Sri Lanka, these can actually be also strong but orangey red, and then under shortwave moderate orangey red, so a slight difference there. And for your Thai rubies, we actually have weak red under long wave UV and typically inert under shortwave. And the reason for these differences is that the stones from Myanmar and also Sri Lanka do not have a high degree of iron content, but the Thai rubies do. and that iron content suppresses the fluorescence within those stones. But to be able to use this and quite categorically say a locality based on fluorescence, I think you would certainly need experience and maybe some master stones, so stones where you know the exact locality so that you can compare the results to be able to correctly identify them. Another example which indicates locality, I've actually got a sapphire here. Sapphires from Sri Lanka and Madagascar, if they are blue, colourless or yellow, actually have this really unique fluorescence. So they actually go this orangey red colour, or what's described as apricot colour, very strongly under shortwave, beg your pardon, very strongly under long wave, and then less so under shortwave. And this is really unique. So just seeing this, if you had a blue, yellow, or a white sapphire and you have this fluorescence, you actually can identify it as being a stone from Sri Lanka or Madagascar. There is one exception to that. I told you that there'd be exceptions. So forgive me, but lots of exceptions in fluorescence. Yellow synthetic sapphires can also show this orangey red fluorescence. It's typically stronger though in shortwave than in long wave. But just to let you know, that could be an area of confusion. And lastly, this is the last area I'm going to focus on before we move on to diamonds. Fluorescence can also be utilized within mining. So I've already given the example of X-rays and diamonds, but also using long wave UV light, you can actually scan with a torch different areas. So whether it might be the walls inside a mine searching for a little seam of a fluorescent gem, or even like in this picture, I was emerald and fluorite mining in Queensland. This is, I was looking for fluorite. So at dusk, I'm on a tailings pile, so an old mine dump, and you can just use a UV fluorescent torch to go around and wait for any of the ground to start fluorescing, and a really quick way of finding your gems. So that's an excellent way of doing it. So a number of gems can actually be mined like this, or we can utilize this method. So opals, white opals, we can do this with. Scheelite, it's quite a popular method for scheelite, ruby as well. It's also a great way of finding scorpions because scorpions all fluoresce like this yellowish green, bluish green colour. So great way of finding scorpions also. And now onto the final section, we're just going to focus a little bit of time on diamonds because diamonds, even though they have a really variable reaction under UV light, in a way, they're one of the more predictable results that we have in regards to testing with UV. So for diamonds, the typical responses, not all diamonds fluoresce, though it's said about a third of diamonds fluoresce. I've also read figures up to 50%, which actually I wouldn't disagree with. So it's around a third to 50% of diamonds will fluoresce to some degree. The typical fluorescence for natural diamonds is blue. So this is the typical fluorescent color. But also we can see white, yellow, orange, green and red fluorescence in natural diamonds also. This will typically be seen in long wave UV light, and then if any fluorescence is in short wave, it will be to a lesser degree. If not, the stone might be inert. And these fluorescent effects will vary in strength, so from weak to very strong. So if we have a look at this picture here, this is actually the Murchison snuff box, which is housed in the Natural History Museum in London. If you've been to London, you may have seen it. And this is a diamond encrusted snuff box here, featuring Tsar Alexander II. Now, if we actually popped this under long wave UV light, we see this. Oh, oh, I'm sorry. Well, let me tell you what you would see. If we were to pop this under long wave UV light, what we would see is a range of different fluorescent effects. Not all of the diamonds will fluoresce. The majority of them do fluoresce blue, but there's also some yellows and greens in there as well. And out of those that do fluoresce, they're going to fluoresce a variety of strengths from weak to very strong. So here are some of our grades for fluorescence. So we go from very strong, medium, weak to inert. Sometimes in gemstones, you will actually see, even on the inert ones, a bit of a purple reflection on the facet surfaces. Don't confuse this for fluorescence. Often this will just be a reflection of the long wave UV lamp. So this can be seen in UV boxes as well, particularly with UV hand torches. So just be warned. Okay, we're really looking for the body of the gem to fluoresce. And it's said that actually fluorescence can have effects on diamonds. So in colorless diamonds, so those that completely lack color, let's say D, E, or F in color grade, if these have a strong or very strong fluorescence, it's said that this can have a really negative effect on the appearance of these diamonds. And it's true, sometimes it can. So sometimes it can make them appear milky and less transparent due to this fluorescence effect that you see. And you can see this even in daylight because of the UV light coming from the sun. Now, in some other stones, so for example, strong medium, you can't see it so much, if not at all. And there have actually been some tests done recently, but by the GIA, there is an article where they actually showed lots of people whether they could tell the difference between diamonds of different fluorescence grades in sunlight. And actually, most of the time they couldn't unless it really was affecting that transparency. But generally speaking, due to the fact that this is quite a well-known fact that it can affect them negatively, and this is in the consumer awareness as well, generally speaking, there is less desire for a fluorescent gemstone. And actually, because of that, because there's less demand, there's also a lesser price on the market for them as well. So you can expect a bit of a discount on these stones, anywhere from around 5% to 15%, I believe. But that might change, it changes all the time. The adverse effect is actually believed to be true for those stones that have more color. So if they have a yellowish tint to them, let's say color grades G to L, the blue fluorescence actually cancels out some of the yellow coloration, making these stones appear more colorless. So this has a positive effect on the appearance of these diamonds, and for that reason, these can actually go at a slight premium. I've read up to about 4 or 5% again. However, I will just put in a little bit of extra information in that. If the stone does have a strong yellow colour and very strong fluorescence, I've also noticed that these can look really milky and almost petrol green, like a really weird fluorescent effect that you see in these stones. So it's not always positive. When it comes to testing diamonds for their identity, so diamonds versus any imitations that are out there, fluorescence can really help us with this if the stones fluoresce. So if the stones fluoresce blue under long wave UV, then straight away you have an identity. It's going to be diamond because the only colorless stone that fluoresces blue under long wave UV light is diamond. Okay, so that can be really helpful. If it doesn't fluoresce, oh, that's a bit harder. Okay, so if it fluoresces blue under long wave UV, excellent, you've got a diamond. This can be really helpful when testing bulk again. So this is actually a mixed bag of melee gemstones. Straight away, I know that there's diamonds in there, and you know there's diamonds in there too, because we can see some are fluorescing blue. And this is under long wave, so therefore there are diamonds within this gem parcel. However, we can't really see it here, but there's also a number of gemstones in here, and I mean a high number of gemstones that are fluorescing a dull yellow. And if I go back to this screen here, dull yellow under long wave UV light, this is actually a mixed bag with cubic zirconia. So it can be really helpful, even actually in cluster rings or any rings that have multiple diamonds. It's really great just to shine your UV torch on, test them in bulk. And if a number are fluorescing, at least maybe a third I would expect to be fluorescing to some degree. And if they're blue, I can be quite happy that they're diamonds. You might want to test all the ones that don't fluoresce though, just in case. Fluorescence can also be really helpful to distinguish synthetics from natural diamonds. This is because their fluorescent behavior differs. So natural diamonds, where they fluoresce strongest under long wave UV light, synthetics are the opposite. They fluoresce strongest under short wave UV light. That is key. That's absolutely key. So obviously, if your diamond doesn't fluoresce, it's not going to help you. But if it does, just take note of what light source is making it fluoresce the strongest, and you can actually conclude whether it's a natural or a synthetic diamond. I will say there is one exception for your natural diamonds, lots of exceptions, and that would actually be your natural blue diamonds. These fluoresce strongest under shortwave UV light, often fluorescing and phosphorescing red. You might think of the Hope diamond because that famously phosphoresces for several minutes, a red glow. In regards to other differences, so natural diamonds, as we discussed, these mainly fluoresce blue in color, whereas synthetic diamonds mainly fluoresce an orange to yellow in color. And that's yellow if it's grown by HPHT processes, and orange if it's grown by CVD processes. And then another feature which can differ between the two, natural diamonds, if they phosphoresce, except for blues, these will phosphoresce after exposure to long wave UV light. Synthetic diamonds, these, if they fluoresce strongest after shortwave UV light. And this can also be key as well. And there are some excellent testing tools on the market. Because as I said, you might be able to identify it just with a normal UV box under long wave and short wave, but there are some really good tools on the market that will test for fluorescence, even in stones that, where we can't see it with our eyes, but the machine can pick up on the phosphorescence after long wave or short wave UV from the stones. So one is actually, there's a Yehuda Sherlock detector. I think it's about $6,000 US dollars. That's excellent for detecting synthetics versus natural. There are also some other fluorescent pieces of equipment that show it really clearly. One would be the Gematrix, which is its own kind of little fluorescent block box for long wave and short wave. This is excellent because this shows you the fluorescence really clearly and allows you to take photographs from your phone and compare the short wave and long wave side by side. So that's about $600. Branko Dejanin, I think he created it. But they're $600, yeah, and they will tell you the majority of the time. It's not quite as advanced as some of the other ones, thus the price difference, but still really handy. Another absolutely diagnostic test for natural versus synthetic diamonds is actually the DTC Diamond View. Now, you can go ahead and buy one of these. I think these are about $20,000, mind you, so mainly it's just for laboratories. But basically, these use very high energy shortwave UV light. And with this high energy, we actually fluoresce within the stones the growth pattern of the stone. And on observation of these different growth patterns, we can distinguish between natural, CVD, and HPHT grown synthetic diamonds. So pictured here is actually a really old version. They look much neater and snazzier nowadays. But on the screen, we've actually got a picture of a diamond here. This is a natural diamond. You can see it's fluorescing blue. And also it's got an octahedral growth pattern within it. So it's actually mimicking the shape of the octahedral crystal that natural diamonds grow in. There are two other patterns that can occur within natural diamonds under this piece of equipment. One is dislocation patterns and the other is just undistinguishable. It's not really a set pattern. So they're the three patterns that tell you that it's natural diamond. All three of these are very different to synthetics. So let's have a look. So here is HPHT. Fluorescent patterns that we see under the diamond view. So these are actually cubo-octahedral fluorescent patterns, and they mimic the shape of the HPHT synthetic diamond crystals that I've pictured here. So the crystals have these truncated corners, either a truncated cube or a truncated octahedron, and we can actually see these truncated edges within the fluorescent patterns itself, letting us know that this is a HPHT grown synthetic diamond. I've even seen these patterns just with a really high energy laser pen, which has UV within it. You have to use this carefully because the diamond really reflects it back at you, so do be careful. But you can actually excite a pattern like this. So this is just like a cross fluorescent pattern never seen in natural diamonds. So this is another way of actually not having a diamond view, but being able to see these cubo-octahedral patterns. I have also been able to do this only on a couple of specimens with just a normal UV torch as well. So that's really cool. And then for the CVD diamonds, where these grow in just one direction, so they kind of have this layered growth, you can see this layered growth pattern within the diamond itself under the diamond view. Also notice that it's fluorescing orange. So there we go. So for a summary of what diamonds fluoresce or how diamonds fluoresce, so about a third of our diamonds fluoresce. This is actually true for natural and synthetics, but for natural diamonds, they vary in color and strength, but typically are blue, and these will always be strongest under long wave UV light. So with this information, we can use it for determining between synthetic and natural diamonds, because natural diamonds are strongest in long wave UV if they fluoresce. Synthetics are the opposite, they're strongest in short wave. We have slightly differing colors as well, the different phosphorescence after the different energies, and also we can have a look for those growth patterns under the diamond view as well. To cover our other learning objectives, so what is fluorescence? So this is the emission of light by an object whilst it's being excited by a higher energy. So what's happening is our invisible high energy light is going into our gemstone, and our gemstone is emitting it as visible light. And depending on whereabouts in the spectrum it emits that light, so what energy wavelength, then that will actually determine the color of the fluorescence. And how can we use fluorescence? Lots of ways. So it can aid us in the identification of gems, but be warned, there are many variances. So really, it's very important that you know where to look. There's lots of times that you can just research a particular thing that you want to know. You know, they'll come up at different times in your life, and you'll know what's important to you at that time for what you need to know the fluorescence of. One time for me during an exam, I really needed to know the fluorescence of amethyst versus purple scapolite. Suddenly that was the most important fluorescence to me in the world, and I still haven't forgotten the distinction between them. Other things that can help us do, identify synthetics and some treatments, also composites. It can indicate locality. We can bulk test with it, and we can test set stones, rough stones, faceted stones, loose stones, whatever you like. And it can also help us with the mining of gemstones. And lastly, it can be used in display. And I've got a couple of bonus slides for you in a couple of slides' time. But for now, that is the end of the main presentation. I'm just going to release a quiz to you to see how you do with it. There's just 4 questions. It should be up on your screen now. And I'll read them out to you. The first one actually might be a bit of a tongue twister. Fluorescence is the emission of light from an object whilst it's being excited by a higher energy, the emission of light from an object whilst it's being excited by a lower energy, the emission of light from an object after it's been excited by a higher energy, or the emission of light from an object after it's been excited by a lower energy. So that's question 1. Pick the correct answer, and then on to question 2. Fluorescence can help identify synthetic gems, treated gems, composite gems. Select all that apply. And then question 3, what is the typical fluorescence of natural diamonds? Choices are variable, usually blue, strongest in shortwave. Or variable, usually yellow to orange, strongest in shortwave. Or variable, usually blue, strongest in long wave. So pick your correct answer. And then the last question about how to test our stones. You should test for fluorescence in the following environment: black non-reflecting background, white shiny background, or a grey neutral background. I've had my first question come in, so I might just quickly answer that because it shouldn't take long. From Ravindi, thank you. He asks, what causes natural diamonds to fluoresce a red colour? Now, the fluorescence in diamonds, every time I've tried to look into it, it seems very complex, but it's going to do with the boron that's within it, and then also potentially the vacancies that are also left within the structure due to that boron being there as well. So it's going to do with that boron in there because boron is a fluorophore, remember? So that's the answer. Very good. So let's go through the test results. I'm just going to close that for you and I'm going to review it as a group because I can review this publicly. So here we go. So we've got a good overall score. So just to run through these as a group. So fluorescence is the emission of light from an object whilst it's being excited by a higher energy. That's the correct answer. So very good. The emission of light after it's been excited by a higher energy is known as phosphorescence. When it comes to question 2, fluorescence can help us identify all of those things. So some synthetics, some treatments, some composites. So it completely depends on what material we're referring to. So it's certainly not a blanket statement, but it can help us in particular occasions. Question 3, what is the typical fluorescence of natural diamonds? The correct answer is variable, usually blue, strongest in long wave UV. And that strongest in long wave UV, really important because that can help us distinguish natural diamonds from the synthetics because they're the ones that are strongest in shortwave UV. And last question, you should test for fluorescence in the following environments: black, non-reflecting backgrounds. That's where you'll see the clearest results. And if you can, it would actually be very, it would be very wise to actually turn off any surrounding lights as well for us. So here, anyone again who's been to the Natural History Museum will know this particular display very well. This is the Aurora Pyramid of Hope, and this is owned by Alan Bronstein. And this actually consists of 296 naturally coloured diamonds, and they're displayed in this pyramid, and they flick the light source between daylight and long wave UV. And so this is daylight and then also shows you that long wave UV as well. So a really cool display of fluorescence in diamonds. Even though they're fancy coloured, we can see they still stick to the rules of natural diamonds. So not all of them are fluorescing. The ones that do, they're mainly fluorescing blue, and we can see a variety of different strengths of fluorescence. So I love this display as well because every time I go, I always hear the revelation of people realizing that diamonds come in other colors apart from colorless. So great exposure for fancy colored diamonds. Here is actually some fluorescent diamonds that are utilized within design. So this particular collection is called UV Diamonds by Maria Cuvadi, and she's actually selected fluorescent and non-fluorescent diamonds and arranged them so she can do this. So that's pretty cool. So if you're in the club, you get a surprise design. So these are actually angels that are depicted on these pendants. So very cool. I've also seen other pendants that are also parveyed, and they do a similar thing, but with initials and things. So again, that's pretty cool. And then other displays, this is a museum really, known as the Crystal Caves, or an exhibition. This is actually in Atherton in Queensland, Australia. Here I am. It's actually a man-made cave. And inside, I don't know how many minerals and crystals there are, must be thousands, all displayed within this kind of man-made cave. It's really quite cool. And you've got some of the world's largest amethysts in there as well. And very, very awesome. But the owner actually put together, it took him 7 years to collect something known as the magic spheres. And here they are. There's many more in the actual display. And he's basically created this really cool fluorescent solar system-esque type display, which all kind of revolves around each other. It's really interesting. They're each one featuring a particularly fluorescent mineral. So again, a really, really cool display. Now we'll actually move on to questions. So if you do have any questions for me, please do put them just to the right here, and we'll talk through some of those now. As always, I'll just answer 3 or 4 now, and then we'll finish the session. And if you want to hang about at the end, I will try and answer a few more questions for you. Okay, whilst I read the questions, I'm going to put on this fluorescent display for you. So sit back and enjoy. I've got a lot of very specific questions here. And I must say that if I haven't looked into that exact gem exactly, because I don't commit my whole life to fluorescence, as you know, I kind of cover all of the various gems that we have and different treatments and things. Some things I haven't looked into. So I am sorry if I can't answer your question, because the very, very specific ones, really, you would have to really focus research purely on that one thing. So just like I said earlier, for me, at one point it became very important to know the difference between amethyst and purple scapolite. Otherwise I'd never go seeking it unless it really meant something to me at that time. But just to let you know where you can look for answers, if you're ever unsure, there are loads of different places, resources. So constantly, for every single thing that I learn, I look into different articles, different books, online articles. I also look into lots of different tables and cross-reference, because actually a lot of them say different things to one another. So it's a lot of research to look into. I do appreciate that, but that's why one person cannot know the fluorescence effects for everything unless they truly, really committed all their time to it, really. But here we go. So let's have a look at some of these questions. I've got some at the bottom here. So I've got one, how about amber? Does this always have a fluorescence? No. As I said, a lot of gems actually vary in fluorescence. Amber, I do know, because I've looked into quite a lot of fluorescence with organics. So some amber can be completely inert, some can be slightly greenish, some can be slightly yellowish, some can be slightly whitish. And then there was a deposit of really cool amber that was found. It was about 2012, I think, that actually had this real bluish white fluorescence that you could even see actually in daylight. So that was really cool. So amber can fluoresce, actually fluoresces a number of different colors to a number of degrees, but can also be inert. Okay, and that can also identify locality, I think, if it fluoresces that blue. Okay. In regards to Maureen, no, I'm afraid I don't have class notes. I'm afraid they're all up there, so I'm afraid I can't actually give you any class notes that I have. However, for some of the previous talks that I've done, I have actually put interesting links to certain things on my website, so on juryadvisor.com. So do subscribe to that and you'll get alerted. And so when I post the video from the YouTube channel, from Gem A's YouTube channel, normally that's where I'll put the references for that lecture or just some interesting references. So do check out for that. Okay, let's have a look. One question, do the CVD diamonds have orange fluorescence with shortwave UV? Yes, so typically CVD diamonds fluoresce orange. They can also fluoresce yellow, green and red, but their most common color is orange, and they fluoresce strongest in shortwave UV. They may also show this in long wave, but just to a lesser amount, or they might be inert. But yes, CVD diamonds, their main color is orange. Someone asks, what's the main colouring agent in spinel? That's an easily Googleable one, but that's chromium, really similar to diamonds, beg your pardon, really similar to rubies. So red spinels and rubies actually have a really similar spectrum, absorption spectrum. Difference is that, well, one of the differences, many differences, but one of the differences is that red spinel does not contain iron. So we have one here. Is the strong green fluorescent diamond a sign that it's synthetic? My question to you would be, where is it most strongly fluorescent? Because you can get naturally slightly green fluorescent diamonds. So if it fluoresces strongest under shortwave, it's going to be a synthetic. Strongest under long wave, it will be a natural. So use all the information to test your bits and pieces. Okay. Does synthetic alexandrite fluoresce? I'm not sure, I've never tested one. I know that natural alexandrite, because it does contain chromium, can fluoresce a weak to moderate red, but because it contains iron, can also be inert as well. I think actually I have tested a synthetic alexandrite, and yes, I think it did fluoresce red. So I think that's the answer, but that might not be the only answer, because like I said, it can vary. You never know, you could dope the alexandrite in iron and quench the fluorescence. So really, you'd have to research to find out the exact answer to that question. Okay, but otherwise, I'm going to pause the questions there. We can always return to them at the end of this session, just so that I can let you go because I have gone over time. And if you have any questions, please feel free to email me if it's about the content of the lecture. So that's Julia at jewelryadvisor.com, Gemme about anything else to do with their courses or anything at education@gemme.com. And just as a reminder, if you did miss any previous webinars, you can actually start watching those now on the Gemme YouTube channel. I've also reposted them on my website as well. Otherwise, that's it. So that's it from me. So thank you so much for joining us for today's webinar on fluorescence. I hope you found it interesting. I hope you found it very enjoyable. If you are in England, I hope you enjoy the rest of your sunny afternoon. Elsewhere in the world, good morning or good night, depending on your time zone. But thank you so much for joining me, and I hope to see you next week for the diffusion of titanium in sapphires. Thank you.